Oh, second marker. Wally's in the lead.
Yeah, Wallace. That's my boy.
You mean that's my boy?
That's your boy. I want to double down. I want to double down on that right now.
Oh, HR, big spender. You serious?
Serious? Serious as a heart attack, Rich.
Guys, they're neck and neck. And almost at the finish line.
Yes! Pay up!
Adab, so this is dedicated to all the Flash fans out there. So you saw the Flash passing through the walls, making the impossible possible. Okay, so let's start. How is it possible? First of all, I'm gonna start with the introduction. So yeah, it's possible through quantum tunneling, and that's what we're gonna go through throughout our presentation. So this is Khuzaima Ali Khan, and along with me, I have Meesum Ali Qazalbash and Jahania Shah. So what are the different topics and agenda for today? So now first of all discuss classical theories, and then we're gonna hop on to the essence of quantum mechanics. What is quantum mechanics and why is it important? And then in the next section, we will discuss the application and experimental evidence in order to authenticate the topic. And lastly, we're gonna discuss the limitation and future iterations in this particular topic, since everything is not perfect, and we have some loopholes in the theory and some technology depreciation, which we're gonna discuss in the next sections. And now I would like to invite Meesum Ali Qazalbash to take over the stage.
Suppose there is a ball on the side of a cliff. What happens if you try to push this ball? Speaking of physics, if the ball has enough kinetic energy to come over the potential energy of the hill, it will fall on the other side of it, otherwise it will come back. We have to keep this experiment in our mind, later we'll talk about it. Now we'll talk about the essence of quantum mechanics. The essence of quantum mechanics really includes things because of the probabilistic nature of it and also the uncertainties. Suppose we have the same experiment in the quantum world, but instead of hill, we have a quantum potential barrier. Instead of ball, we have a quantum particle. It is found that when we try to hit that quantum particle with the potential barrier, it will sometimes form on the other side of the barrier. This is not the case in the classical physics. For the better representation, here is the diagram, and the diagrams very much say about the name of the art subject, is quantum tunneling. It is that the particle has tunneled through that barrier and reached on the other side. If you talk more about the Reader's approach towards solving this problem, then would end with a wave function that tunnels throughout the barrier, as shown in the figure. As the wave function collides with the barrier, it reflects back, but also a small part of it transmits through a barrier and decays in the process. In the end, we get a very small but non-zero wave function on the other side of the barrier. It's as if the particle has tunneled through that barrier, and hence the name quantum tunneling. Particle has tunneled through that barrier, the other side of the barrier. Now we will talk about some applications of the quantum tunneling. Foremost are the quantum logic gates. Quantum tunneling is an essential part of many fundamental quantum logic gates, like phase gate and CNOT gate, which full form is controlled NOT gate. As quantum gates are building blocks of quantum computers, therefore quantum computers uses quantum tunneling. These quantum gates uses quantum tunneling to create entanglement and also mutate the electrons around the magnetic field. In this thing, the quantum tunneling plays a crucial part because the rotation of the electron must be adiabatic, which means that electrons should be in their ground state, otherwise they will tunnel to the other side of the value. In this case, we may lose information. Now to the Jahania Shah.
Okay, so hello everyone. Moving towards the next fascinating application of quantum tunneling. Here I mean tunneling diodes. So it was invented in 1958 by Leo Misaki, who received the Nobel Prize in Physics in 1973 for his work on the tunneling effect used in these diodes. So let's come to its operational part. That the operation of tunnel diode is basically based on quantum mechanics principle known as quantum tunneling, which refers to the direct flow of electrons across the small depletion region from the conduction band of the n side, this is n side, to the valence band of p type, that's p side. The depletion region is so narrow so that electrons can tunnel through it even if they don't have enough energy to cross the energy barrier, such as in normal diodes. This results in negative resistance region in the IV curves, which we'll be discussing in next slides, which means that as the voltage across the diode increases, the current through it decreases. Although in a normal PN junction diode, a wide depletion region acts as a barrier that opposes the flow of current, and we need sufficient amount of voltage that needs to be applied to overcome this barrier. However, in a tunnel diodes, the narrow depletion region allows for the flow of current with a small supplied voltage. We'll see the significance of this small voltage in the coming slides. The energy current gap is an important concept in tunnel diodes. In normal diodes, electrons needs to have enough energy to cross the energy barrier between the conduction band and the valence band to move from the n-type material to the p-type material. However, in a tunnel diodes, the energy barrier is so low or very small so that electrons can tunnel through it even if they don't have enough energy to cross the band gap. Okay, so let's just analyze the IV curve of the ordinary diodes. For the starting point, it rests for some times until sufficient amount of voltage is applied, that is VTH, threshold voltage, after which it starts conducting currents. However, this is not the case for tunnel diode. The IV curve of tunnel diode is unique because of its negative resistance region. As the voltage across the diode increases, the current through it initially increases, but then it reaches its peak and it starts decreasing. This is because of tunneling effect. In contrast to the IV curve of a normal diode that does not have a negative resistance region. This part is is due to the negative resistance, which we say that current is voltage is increasing, but current is decreasing. Now let's move to Khuzaima Ali.
So thank you, Jahania, for the takeover. So we're gonna start now. So we're gonna start with the experiment which proves the quantum tunneling. So the experiment is pretty common to us, and we have done this in O levels in matrix, and you all will be surprised. That is alpha decay. So first, what is alpha decay? Alpha decay is a type of radioactive decay which happens when the neutron when the proton number exceeds 82, and the neutron number should be approximately 210 or greater than 210 of an atom. So here we have taken uranium 238. So you can see the reaction alpha decay on the right side of the screen. So uranium decays and forms the other daughter element along with the helium element. So where is the helium particle actually before the fission takes place? So it is inside the nucleus basically. So it is confined by the nuclear potential, which doesn't allow it to leave until and unless we bombard it with a neutron to let the fission process occur. So the alpha particle, in order to omit or get out of the uranium particle, should have some potential energy. So that should have kinetic energy to escape the potential barrier, because there is a boundary which keeps it together, which bounds it not to exceed, not to get out. So alpha particle is already present in the nucleus, which possesses kinetic energy, which it utilizes to escape the boundary. So now the how and the what if. So now on the right side of the screen, you can see the potential function of the uranium atom during this process. Okay, so the alpha particle which is emitted during the process of fission of uranium has an energy of 4.2 megaelectron volt, which on the diagram you can see as a Q dotted line. And the energy, and also the maximum energy of the potential is B, capital P, which is approximately 26 megaelectron volt. Okay, so what if people thought, what if we bombard uranium with an energy of approximately double amount? So logically it should submerge and combine with the uranium atom, but it doesn't happen. What happens actually is the path which is shown on the diagram. It strikes the potential function and bounces away. So basically it scatters away, which doesn't make sense in classical physics. So along with those lines, you should also notice that an atom can act like a particle and a wave also. The alpha particle was able to pass through due to quantum tunneling. So you can see the diagram also. You can see the waves hitting the potential function, and the potential function has enough energy that it does not die off during the barrier, and some of the parts of the component of the wave function scatters and passes through the barrier, and you can see that helium occurs due to the fission process. So this paradox was resolved by Gamow in 1928, which utilized the idea of Euler quantum tunneling. So let's understand this more. Okay, so what happens? Okay, so let the animation end. Okay, so yeah, so you can see I have used some animation of the atoms. So let's imagine on the left side of the potential function that is a wave function. So that let's imagine that are helium atoms which are what you say hitting the potential function of the uranium to escape. Okay, so you can imagine there are a lot of them. The wave function hits approximately. Let's take an example. If the speed of the wave function is 10 to the power 7 meter per second, so approximately it's gonna hit the wall approximately 10 to the power 21 times in a second. So if you find the probability of a single atom hitting the wall, that is 1 over 10 to the power 21. So you can imagine a lot of atoms are hitting the potential function at a single time. So there are chances that one of them can escape the potential function and pass through it and escape the entire potential barrier. So moreover, this diagram shows the dual nature of the atom, also the wave as well as the particle. The wave nature of the entire atom leads to the potential wave function passing through the entire barrier. You can see that the wave doesn't die off during the potential barrier. It decays in magnitude, but on the other side of the wall it passes away and retains the original shape, but a decreased amount. On the other hand, the quantum nature of the atom can be seen and observed during quantum tunneling. So this is the particle nature which allows the atom to pass through, and voila, we have helium at the output. So now I would like Jahania Shah again to take over the stage and list out some limitations and future directions. And I hope that you got some understanding about the concept. Thank you.
Okay, so now let's move to some limitations and future directions of quantum tunneling. Let's discuss. We have discussed that quantum tunneling is a powerful phenomena that has important applications in quantum computing and other fields as well. However, it also poses several challenges and limitations that must be addressed in order to build reliable and efficient computing systems. So we have highlighted three limitations for quantum tunneling. So one of the major challenges is the difficulty of controlling and manipulating qubits that are subject to quantum tunneling, because tunneling occurs spontaneously and unpredictably. It can be difficult to precisely control the behavior of qubits that are tunneling. This can also lead to errors in quantum computing operations and make it challenging to design reliable quantum computer hardware. Another limitations which we have studied is the potential for decoherence and loss of information due to tunneling. Decoherence occurs when the quantum state of a system interact with its environmental factors, leading to loss of information and the collapse of quantum states. Because tunneling can lead to interaction with the environment, it can also lead to decoherence and the loss of quantum information. In addition, the use of tunneling in quantum computing hardware can also be limited by the physical properties of material and the presence of noise and other environmental factors. For example, superconducting qubits, which are commonly used in quantum computing hardware, are sensitive to fluctuation in temperature and electromagnetic noise, which can interfere with tunneling, and it can also lead to some errors in quantum computing operations. While quantum computing has the potential to revolutionize computing in other fields, its limitations must be carefully considered and addressed in order to fully realize its potential. Oh my god, I'm looking everyone zone out. Let's pick up the pace here. I don't want to bore you guys all to tears. So, just the last slide of this whole presentation, just looking to the future, we have explored some possible development in the field of quantum tunneling, including enhanced control and manipulation of tunneling probabilities, the use of tunneling for quantum information processing, and experimental advancement in observing and measuring tunneling phenomena. In terms of enhanced control and manipulation of tunneling probabilities, researchers could potentially explore the use of novel materials and structures to engineer potential barriers and wave functions with greater precision. Regarding the use of tunneling of quantum information processing, future research may focus on utilizing tunneling to develop more efficient and reliable quantum devices, as well as investigating the potential of tunneling-based quantum gates and algorithms. And the last one is experimental advancement in observing and measuring tunneling phenomena will help shed light on the fundamental nature of quantum systems and potentially lead to new discoveries and applications. Overall, these potential developments in the field of quantum tunneling hold great promise for advancing understanding and application for this fascinating phenomena. Here, I would like to thank you for your attention, and I hope that this presentation has deepened your appreciation for the complex and exciting world of quantum mechanics. Once again, thank you for hearing us.